This video is the first of many discussing Olympiad inequalities. And these are a very common type of problem on Math Olympiads. And in this video, we're going to be exploring the fundamentals of Olympiad inequalities, like basic techniques to solve the easiest problems, and then we're going to build up from there. And so we first need to define what even is an Olympiad inequality. So they're all usually of the form given X information about the variables, which are usually all real numbers, prove Y is greater than or equal to Z. And each of these are expressions in terms of the variables. So Y could be something very complicated, Z could be constant for all we know, and X could be given absolutely no information at all, other than that they are real numbers. And we're going to be exploring how to solve problems of this sort. So, how do you even prove an Olympiad inequality? Well, I'm going to present to you a very trivial fact, one that seems so obvious that you might just gloss over it, but this will bring us a long way. And it is this following fact. If x is a real number, then x squared is greater than or equal to 0. And this is our fact. And this is true because positive times positive is greater than or equal to 0, and negative times negative is also positive. And equality here holds when x is equal to 0, because that's the only number whose square is 0. And even though this is super obvious, this is so important that mathematicians even gave it its own name. It's called the trivial inequality. So whenever someone mentions, oh, this is true by the trivial inequality, now you know what they're talking about, because now you know that all squares are non-negative. So how will this even help us at all? If I go ahead and write the following square, so x minus y squared is greater than or equal to 0. Now we've introduced two variables into the picture, and you'll see why I made this choice of variables here and why I put the minus sign. So, and expanding this out gives x squared plus y squared minus 2xy is greater than or equal to 0. And therefore, x squared plus y squared is greater than or equal to 2xy. And this is our first fact from using that squares are non-negative. And we're using the fact that equality holds if x is equal to y. And that's very strong because that gives us another way to obtain equality cases. And in fact, this is the simplest form of an even more general inequality, which I'll get to in a bit. So, and to introduce it a bit, we can rewrite our inequality as x squared plus y squared over 2 is greater than or equal to xy. And maybe we can write x squared is equal to its own variable and y squared is also its own variable, so that we can don't have exponents over here and all the exponents get concentrated over there. So let's let x squared equal a and y squared equal b. Then we have that a plus b over 2 is greater than or equal to the square root of ab. With equality holding if and only if a is equal to b and x squared is equal to y squared. This is the simplest form of what is called the AMGM inequality. And can we generalize this to more variables than just two? Because using two variables is kind of boring. Well, yes, we can. So suppose that a1, a2, all the way to an are non-negative real numbers, so they can't be negative. Then a1 plus a2 plus all the way to plus an over n, which is known as the arithmetic mean of the numbers, is greater than or equal to, and now we want something with their product, and we want to have it degree 1 because this side is degree 1 as well. Because if we have 1 degree 1 and 1 degree 2 over here, then we can make one side very skewed and the other one really small. So we want this to be degree 1 involving the product, and the most obvious way to do so is to put an nth root. So we have a1, a2, all the way to an. And we made use of the nth root because we have a degree n thing here, and we want to still involve the product, so we just raise it to the power of 1 over n. And this is called the AMGM inequality, its most general form. Actually, not its most general form, as we will see in a bit. I won't prove this inequality in all its glory in this video, but if you're interested in the proof, I'll go ahead and just give a brief outline in a pinned comment. All right, so now that we have this in our toolbox, let's see how we can apply it to our first Olympiad inequality example. So our first example is if A, B, and C are real numbers, prove that a squared plus b squared plus c squared is greater than or equal to ab plus bc plus ca. All right, so this doesn't really look like AMGM because if we try using a squared plus b squared plus c squared on and directly use AMGM on this, we just get like ab 3 times the cube root of a squared b squared c squared is greater than or equal to ab plus bc plus ca. We want to prove this, but then if we use AMGM here, it just goes the other direction, and that's bad. So will AMGM work here at all? Actually, it will, because if we can apply AMGM in the following way: a squared plus b squared over 2 is greater than or equal to ab. And then you can probably see where I'm going with this. And then finally, c squared plus a squared over 2 is greater than or equal to ca. And then you just add all these inequalities, and you're done. All right, so where the heck did that come from? Like, why are we supposed to, and how are we supposed to motivate considering each term, two terms one by one? Well, we have this ab term here and a squared plus b squared over there. So our most natural method is to combine them in some sense. So we can get like a squared plus b squared gives it something into ab, and then you cyclically sum to get the result. All right, so now we can go ahead and talk a bit more about our next example, and maybe this will be slightly more motivated given the above. So now a, b, and c are positive real numbers. So now we must prove that, let me go ahead and separate this out, plus b cubed plus c cubed is greater than or equal to a squared b plus b squared c plus c squared a. And we want to somehow find good motivation for doing so, if an AMGM will suffice. So, motivated by our above analysis, we have this a squared b here, and a squared means we want to have two a terms in our AMGM, because over here, if we have two a terms, then we get like a1 squared over here. So, and that can make the degrees asymmetric if we use AMGM on the same variable. twice in a row. So given the a and b here, what if we try applying AMGM on a cubed, and b cubed, because that exploits the asymmetry. So let's try it out. So we have a cubed plus b cubed over 3 is greater than or equal to a squared b by AMGM. And we get similar inequalities for the other ones, namely b cubed plus b cubed plus c cubed over 3 is greater than or equal to b squared c, and then c cubed plus c cubed plus a cubed over 3 is greater than or equal to c squared a. And summing these guys will finish. And we don't really need to sum these guys manually in order to get the result, because we know that equality holds in everywhere. So equality holds when a equals b, then b equals c, then c equals a, and equality here holds when a equals b equals c, and therefore summing these should give this result. Otherwise, it will give something even weaker or even stronger on that matter. All right. So when can we use AMGM to solve problems like this? Is there a general theorem that tells you when it is possible to use AMGM to solve these type of problems? Well, yes, there is. And the underlying theorem is known as Muirhead's inequality. So suppose we want to prove this inequality here. And when I mean symmetric sum, I mean the exponents run over all permutations. So we would have this term here, and then x1 to the a2 times x2 to the a1, and so on and so forth, and going over all permutations in the exponents with multiplicity. And you want to show that it's greater than this guy over here. So when can we get away with AMGM? Well, the theorem from Muirhead states that if you know that a different pen, so a1 is greater than or equal to b1, a1 plus a2 is greater than or equal to b1 plus b2, and so on, all the way to a1 plus a2 plus all the way to plus an minus 1 is greater than or equal to b1 plus b2 plus all the way to plus bn minus 1. And finally, a1 plus a2 plus all the way to plus an is equal to b1 plus b2 plus all the way to plus bn. If these conditions hold, then Muirhead's inequality states that we can get away with AMGM. And I won't be providing a proof here, and because the proof is very complicated, but now you know how to recognize when AMGM can solve the problem. So, and by the way, there's a shorthand notation for this. We say that A1, A2, all the way to AN majorizes B1, B2, all the way to Bn. Because, and we denote this as this, that means majorize. And basically, if A1, A2, all the way to AN majorizes B1, B2, all the way to Bn, then if we want to prove this inequality here, we can get away with AMGM. Notice that if the Muirhead condition does not hold, that does not mean the inequality is not true. We'll see examples of this in a later video. But for now, we have this AMGM and Muirhead toolkit in our box, so let's look at another example. And now we're going to use our first given that type of condition and introduce how to get around that in most cases. So given that ABC is equal to 1, prove that a squared plus b squared plus c squared is greater than or equal to a plus b plus c. And we're assuming that a, b, and c are greater than or equal to 0. So this immediately looks really complicated off the bat. Like, how are you even supposed to start? And how are you supposed to use this condition here? Well, notice how these two sides are of different degrees. So could we skew it so that A, B, and C are really small so that this doesn't hold? Well, this is where this fact comes in. And we're going to use this fact here to get the degrees to be equal to each other so that both this side and this side have degree 2. This side already has degree 2, so we just need to multiply this by something of degree 1 and we're set. And this is of degree 3, so this is 3, 2, and 1. So we need to multiply this by 1/3 of 3. And this immediately gives the cube root of ABC. And this cube root of ABC, it's equal to 1, so it doesn't change it. And in a theoretical situation, if ABC is equal to 9, or actually 8 in this case, then we'd have to fix this so that we multiply by ABC, cube root of ABC over 8. Because that way we don't multiply the inequality by 1. Alright, with that out of the way, now this is our inequality. But wait, you may ask, isn't this more complicated than original inequality? Because we have a squared plus b squared plus c squared and abc, and those are all integer powers. But why the heck did he throw cube roots in there? Well, the reason why I did this is because this is what the inequality is really asking. Because now we've gotten rid of this condition, because we can literally just erase it now. This is what the inequality wants us to prove. And we're just want to prove a special case where ABC is equal to 1. And both sides have the same degree. And now we can try applying tools like AMGM and Muirhead. So this expands to a squared plus b squared plus c squared is greater than or equal to a to the 4/3 b to the 1/3 c to the 1/3 plus a to the 1/3 b to the 4/3 c to the 1/3 plus a to the 1/3 b to the 1/3 c to the 4/3. And since we don't have 6 terms on each side, as we should have in the symmetric sum, let's multiply both sides by 2. Then one can notice that we indeed get the symmetric sums. So we get the symmetric sum of like a squared, then b to the 0, c to the 0, because we want to get it into the form of Muirhead to see if we can finish by that. And it's greater than or equal to symmetric sum of a to the 4/3, b to the 1/3, c to the 1/3. So we can only hope that this sequence here majorizes that one. And indeed, 2 is greater than or equal to 4/3, 2 is greater than or equal to 4/3 plus 1/3, and 2 is equal to 4/3 plus 1/3 plus 1/3. So AMGM will fit the bill. And from this, we just need to look at each term of this sort, and we want to get A to be weighted 4 times as much as B and C, and a bit of an experimentation yields 4A plus B plus C over 6 is greater than or equal to, or 4A squared plus over here is greater than or equal to A to the 4/3, B to the 1/3, C to the 1/3. Because this is a squared plus a squared plus a squared plus a squared. And then we just sum this cyclically to finish. And we are done. We have solved our first example. And this technique of making everything of the same degree is called homogenizing the inequality, because you're making everything the same. All right. So with this said, notice how we're weighting the terms of the AMGM here. And this gives rise to something more general about AMGM. And again, I'm not going to prove this, but you can basically connect it to all the other AMGM applications we've seen in this video. So basically, W1A1 plus W2A2 plus all the way to plus WNAN, where A1 all the way to AN are greater than or equal to 0. W1, W2 all the way to Wn are greater than or equal to 0, and their sum is equal to 1, so they're like weights, is greater than or equal to AN, A1 to the W1, A2 to the W2, all the way to AN to the Wn. And this is the weighted AMGM inequality. And if W1 is equal to W2 and so on and so forth, we get our standard AMGM inequality. The proof requires a bit of calculus, so I'll omit that. But see if you can connect this inequality here with all the other applications we've seen in this video. And since we discussed AMGM, Muirhead, and homogenization, three of the most important techniques inside Olympiad inequalities, I'll go ahead and conclude the video for here. So thank you so much for watching this video. See you in the next video. Please subscribe if you'd like to see